Hi there, this is Amir from Simra Tech, and today I'm showing you how our agents can learn your verification flow, run your test benches, and report it back to you. As the test bed, we are using a sorry DC. It's done by Manuel Moser on an OpenPDK called Sky 130. And we cloned this design and opened it in our workspace. It's a really complete design, post layout. And now I'm just going to go ahead and open the top level test bench. So how Simra works is that it looks into the source files and will use the appropriate software to open the schematic. In this case, is XGEM. It's an open source. All right, the test bench is open. It's quite an elaborate test bench. We can see all the stimulants. Here is the top level test bench. We have a bunch of CDAC arrays, SAR logic. On the output, we can see we have a comparator latch. If I go in, you can see the comparator latch is actually a preamplification. And also we have a strong arm latch. And now I like to be able to characterize the comparator latch. So I'm just going to go ahead and open the comparator latch test bench and run it. Right, the test bench is open. We can say this is the same block that we want to characterize. We can see the setup. It's an FF corner. All the parameters are set for the simulation. And we can see that manual also included a conversion time table across PBT. And now Simra is trying to run the netlist and run the simulation with ngSpice, which the results are in. We can see all the waveforms that we had in the script to which of them to plot. And I cannot measure directly the conversion time, so I'm going to go ahead and ask it to measure conversion. So now we can measure the conversion time. We see how it measures it and verify if we get the same results as. All right, so the plot is out. We can see the conversion time. It measured 1.7 nanosecond, and this is between the rising edge of the clock and the falling edge of the trigger. And this is done for the condition of TT, nominal temperature, and differential input voltage of 10 millivolts. And looking at the results here, I want to see if we match the references. So I'm including that we have the references measured by Manuel Moser, and if we are matching that, and if not, what's the reason? So the results are in. It's quite interesting. It extracted the references table from here. It built a PVT sweep, and then it ran it across the 9 corners, and then it compared it with the previous results. And it in the middle, it realized that for some of the corners, it doesn't get into a decision. The comparator doesn't have the output for the 10 millivolt input that we have in test bench, but it didn't switch. So for 3 of them is actually failing. And for the SS, we are slightly faster than what was recorded. And also in the FF corners and TT, we can see that the time that we measure is slightly higher. And to analyze what could be the issue is that Manuel used the PDK from 2022, which had a lower VT, and we are using the latest PDK from this year, and therefore there are some discrepancy, and probably this PDK is more close to silicon accurate. So now that we know that this current design wouldn't probably work with the current PDK if we are to tape it out, then we need to redesign this. So I'm going to ask Simra to fine-tune this comparative design for us to be able to meet the spec across PVT. All right, so the results are in. It did make 3 revisions to redesign this. And you can see here the original sizes and redesign sizes. Here we can see that the input LVT devices of the preamplifier increased by 125%. The tail increased, and we had a slight for the cross PMOS small size changes, and the precharge decreased actually in size. And we can see that now after the redesign, it meets it across all the corners and fairly faster than the original design. However, still at the common mode voltage of 700 millivolt SS and cold, it fails. And it identifies as a fundamental limit. It seems that with the update of the PDK, the threshold voltage is actually lower. And with the 700 millivolt and a threshold of close to 500 millivolt, we don't have enough overdrive to be able to have a fast enough decision in the latch. And it suggests that to go forward, then we can have a complementary and also add the PMOS. So in this case, I would say like it really depends on your design. If the VCM of 700 is really a critical spec for you to meet, then we need to consider it. If 700 millivolts wasn't needed, then I think the old design would still satisfy and we didn't need the redesign. But anyhow, we did the redesign. So now that we have this, one thing that now I like to also see is the noise and offset of this comparator. It's not in the test bench, but we can ask it to create a test bench for it and include the references, how it's doing it to measure the offset and noise. And we can also see that. All right, so the results are here for offset, noise, and mismatch characterization. Here you can see for the comparator latch, it did a systematic offset measurement. It has this slow transient input, and it measured it at minus 18 millivolts. And also it ran the Monte Carlo just for 10 points to be a little bit faster to be able to measure it. And for the noise, we can see how it measured it, the thermal noise, KT over noise, total noise, and also it included the references of how it calculated from it's basically papers from TCAS, and it also explained the noise methodology that it used for each of the extraction, and included the dedicated test benches, the spice net test for each of them that can be rerun. So now that we have this, I want a full report for this block characterization. If you have like a specific type of report format, you can give it as a reference, then it will do it exactly how you expect it to have the same fields as you want. Well, here I'm just going to ask you to create a report from stuff it figured out so far about this block and the characterization. And just one thing while it's doing the report, I saw that it made an estimate for the GM. If we look into this session, we can see that it has a problem with measuring the GM because it's a mixed signal block. So the DC operating point wasn't giving exactly something. And in transient, when it sampled it, it wasn't tried region still because it's a dynamic latch. And eventually I told him like, we cannot settle for your GM estimation. You gotta make a real. And now it's figuring out, okay, the way I can do it is that I need to make a dedicated test bench for it, set the DC voltage, and measure it just to get this GM. And it will gonna get the GM, and if it needs, we'll update the results for the noise, and afterward we'll finish the report. All right, so the results are in. We can see the full report is about 10 pages. It included all the characterization, the characterization summary, where all the files are, where the test benches are. Netlist is what are all the parameters that are changed, the corners, temperature, the model of the PDK, the binaries of the simulation, the schematic, and also it has also device inventory. And here we have the PVT characterization. It has the redesign and where the new design is, and the design rationale, how it changed it, and afterward the report of what passes. You can see also the simulation results for PVT. You can see the statistic offset. Here it talks about the measurement method, how it did it. We have the real GM measurement, is another estimate, and use the transfer function to be able to measure that. And also it got the CGG as well to be able to have the noise analysis. And it included all the stuff, the references, what it used for this type of measurements. And at the end, it has about 2.9 LSPR. And yeah, this is the Monte Carlo results, which is running for 10 points. But you can see all the stuff is included. And if there is anything else you wanted to add to it, you can just ask for it. If you want a schematic for test benches, you can ask for it and it makes a copy for you. And the point of this agent is not like a black box that you click or give one prompt and it goes off. It is you can go step by step to verify everything that it outputs. And what we try to minimize the hallucination for AI and generally LLMs is that these LLMs are in a loop that have access to tools, and these tools are the EDA functions on your server. It's the simulation, it's the SPICE simulations, and the output that it gets. And all these results are generated by those softwares, the commercial ones you're used to. And probably in your case, it would be a little bit different from here. You can see we tried it on XGEM and on ngSpice. ngSpice has some limitations. It doesn't have proper noise setup, but in commercial ones, you can do a really proper one. Probably you already have your test benches, so you can reference that. And as well as this open PDK had a lot of changes through time. Maybe you're working with more stable PDKs, but again, you might need some re-specification. You can guide also the agent to do the resizing according to your knowledge. And Simra is designed in a way that it can learn from this process. So now that we did all this, like a half an hour session to characterize this, what we can do is that, okay, we can say to create a workflow skill out of this. So you don't need to go step by step to say, you need to measure the noise, you need to use the real GM and so on. Like to get this report from the beginning without going through any single step, we can create a workflow. And next time, I'm just going to do look at the report and all the artifacts that it reference, all the files, and then you can go in and if needed to adjust it further. So create a So I asked to create a workflow skill for next time we characterize a mixed signal like this. So I assume that because it's a mixed signal, it's a little bit different characterization, the type of stuff we want out of it. You can be more specific. You can be like create a workflow for me for a comparator in an ADC. You can be for an analog device. It can be for a digital device. You can be specific with your workflows. You can give a specific names and ask for a specific workflows to be loaded. And what it does now, it goes through all the session we did and it creates a workflow. So it knows that, okay, if the user wants this block characterized to get the baseline, this is what I'm going to do. And if I see I'm not meeting the spec for any reason, I'm going to go to the user, tell them, okay, I couldn't reach this, probably the PDK changed, or there are some other elements that changed, and therefore it brings you to the loop. Then you can see how you want to redesign it. So yeah, I'm not going to wait for this skill to be created, but you get the gist of it. And if you like to try it out, we can give the same experience to you. You can run it on a sandbox. It's an open source design and software. And yeah, with that, if you have anything specific you want to see, let us know. We would be happy.